In this video, we'll cover the problem keys in rooms. Here, your input is just going to be a single 2D array that represents a set of rooms that you are trying to enter. So with this example, we have a total of 5 rooms here, indexed 0 through 4. Each of these subarrays that you can see, like this one containing 1 and 2, or this one containing 3 and 4, contain keys. So these numbers here are keys. They tell you what room you can access from the current room. So if you're currently in room 1, you can access rooms 3 and 4 because you have their keys present in room 1. By default, you have access to room 0. So your job in this question is to figure out if it's possible to visit all of the rooms that are present here, starting from room 0. If so, you should return true, otherwise you return false. In this case, the output is true. If we start from room 0, obviously you can always visit room 0, so that one we can mark off. You can visit rooms 1 and 2, so those can be marked off from room 0. Once you get to room 1, you can visit rooms 3 and 4, so you can mark those off, and now you can see that every room can be visited starting from room 0. So that is why the output is true in this case. At first glance, this question may not feel like a graph problem or more specifically a DFS problem, but I want to show the underlying graph here in hopes that that might clarify how a DFS makes sense. So we have a bunch of rooms, and then we have these sort of relationships between rooms. We understand that room 1 and room 4 are in a way connected because we can go from room 1 to room 4, but not the other way around. That might sound a little bit like a directed graph. So we can start by trying to model out this scenario as a directed graph and see what happens. So I'm going to go ahead and create this circle, and we know that there are 5 rooms. So let me just start by making 5 of these. Oh my goodness, I don't know why that went over there. We'll have 5 of these rooms, and we'll order them and put them in the correct location in a minute, but we have 5 rooms. Now what we can do is use these keys to draw edges between our rooms. So we know that let's go ahead and label all of them. So we'll say 0, I can make it bigger, 0, 1, 2, 3, and 4. This is sort of arbitrary right now how I've numbered them, it doesn't really matter. We know that from room 0, you can get to room 1. So we have a directed edge from 0 to 1. We also know from room 0, you can get to room 2. So we'll have another directed edge going from 0 to 2. Then we know that from room 1, you can get to room 3. So we have a directed edge in that direction. And similarly, from room 1, you can get to room 4. So we have another directed edge. And that's it. All these other subarrays here are empty. So these are all the edges that we need to model in our graph. So really what our graph is showing is we have our nodes or vertices as the rooms in this problem. And then every key is a connection from one room to another room. So that's like an edge in our graph. Now, really all this question is asking is, if we start at the 0 node in our graph, can we traverse and touch every node present in the graph? That's not too complicated to do using a standard traversal technique. You can use a BFS or a DFS here. It doesn't particularly matter. For practicing DFS, we're going to use DFS here though. Now, you'll remember earlier that when we walked through the example, I checked off each room as we visited it, so that we could track which ones we've already visited. That's analogous to what we've seen before, where we'll keep track of a visited array that'll look like this, that has one position for each of these rooms, and it'll be all false at first. And as we visit rooms, we can go ahead and update them to true. That's not too new. We've seen that before, but we can update this room 4 to true whenever we hit it. So the way we can solve this question is we will just start at the 0 node and have our visited array. we will traverse the entire graph using a DFS, a depth first search. And every time we hit a node, we're going to update it in our array to be visited. You know what? We can actually go through the example here. So let's make all of these false, right? When we first start out, nothing has been visited. Now we want to start with the 0 node here. The first thing we want to do is say, all right, now we can say this node has been visited, which means that we can reach it. Now we want to go look at the neighbors of the 0 node. In other words, what rooms can we get to if we're in the 0 room using the keys that we have? So we can go down the 1 path or the 2 path. Let's go ahead and say we go down the 2 path first. So we go down to 2 and we say, or you know what, actually, no, never mind. Let's say we go down the 1 path first. So we go this way first. We go to the 1 node and we say, all right, mark that as true. We have visited it. Then you repeat the process. You say, look at my neighbors, and then you go pick one of them and go down that way. So let's say we go down the 3 nodes route, so this way. You go over here to the 3 node, you mark it as visited, and you repeat the process. But 3 doesn't have any neighbors. You can't go anywhere from 3, so you can stop. Now we go back to 1, and we ask, all right, what other neighbors do I have that I can explore? We go to the 4 room and mark it as visited, so we'll say true over here. Similar situation here. We don't have any rooms we can go to, so we go back to 1. There's no more neighbors to explore from the 1 node, so we go back to 0, and now we finally go to 2 and mark that as visited. When we get to 2, we check for any neighbors. We realize we don't have any, so we go back to 0. At 0, we realize we don't have any more neighbors, and we're done. The way we're going to implement this is using a stack, like we've seen before, and I'll leave the details of that for when we get to the implementation. In terms of how we know that you should use a DFS for this question, the way you can know that is just because you want to traverse the entire graph, right? Or at least try to traverse the entire graph. You want to check if it's possible to visit all of the locations that are present here, and a DFS is one way of traversing the graph. I want to be clear that you do not have to use a DFS for this question, and it's not necessarily better to use a DFS. A BFS, a breadth first search, is totally valid here as well. It's not really worse in any way. I just wanted to teach a DFS here, and I thought this was a good example of how you can use a DFS. It's not necessary. With that being said, let's go ahead and talk about our time and space complexity. This is nothing too new. It's going to be O of V plus E. You know what? I forgot to start by defining the variables. V is going to be the number of vertices in our graph, which is also equal to the number of rooms in our graph. And then, oops, that got a little messy, rooms. Let's just rewrite that word. Number of rooms. Okay, and then E is going to equal the number of edges, which is also equal to the number of keys that are present in the input 2D array. So, to be clear, in our graph we have 1 node for every room, right? This 0 node represents room 0 up here. So, V, which is the number of vertices or nodes, is the same thing as the number of rooms. Each edge here comes from a key, right? This 1 that I'm circling on the top left of the screen corresponds to this edge right here that takes us from the 0 node to the 1 node. Because it says that starting from room 0, you can access room 1. So every key corresponds to 1 edge, so the number of edges equals the number of keys. Our time complexity is going to be O of V plus E, because every node has to be added to our stack at some point in time. In other words, we have to process every single node or room that's present here at some point in time if we do end up traversing the whole graph. It is possible that we cannot traverse the whole graph. We can only traverse some portion of the graph. And in that case, there's no V here. We don't need a V in the time complexity, necessarily at least. But in the worst case, we do traverse the whole graph, which is a pretty common case. So we do need this V right here. The E, we understand as well. We've seen this many times. For each node, you're going through all of the neighbors of that node. which means that in total, not at one iteration, but in total, you go through every edge in the graph in the worst case. So assuming that you go through the whole graph, you have to touch every edge. That's the time complexity. The space complexity is going to be O of V. There's a couple of reasons for that. The first is our visited array that you can see up here has one element for every room, or one element for every vertex in the graph. So that's O of V space complexity. We also know that if we had a graph that was like this, let's say our 0 node is in the center and then we have a bunch of nodes around, if we had a depth first search. Sorry, I was thinking of the worst case scenario for a BFS, but we want the worst case scenario for a DFS. So you can imagine if we had something like this where you have the 0 node that connects to all of these different nodes and they connect all to each other, you would go all the way down one path and you would have the entire graph, which has V nodes or V rooms. The entire graph would be on your stack at one point in time. So you'd have a worst case space complexity of O of V. Okay, that's all for the complexity, for the complexity and for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I have our example input here that we've seen the 2D array containing all of our rooms and the keys that each room has access to. Here's our function defined, and we have a simple test so that when we're done, we can verify if it works. Now, we know what we want to do is we want to DFS through the entire graph to the entire set of rooms. We want to track what's visited and then make sure that everything has been visited. So we definitely need a visited array here, and it's going to have the size of rooms.length. That's just going to say for every room we want to have one position in our visited array. That way, in the end, we can make sure that everything has been visited. Now we want to DFS through our graph and track which rooms can be visited and which rooms we do visit as we do our DFS. So we're going to create our stack as usual, and we know that we always have access to room 0. You can always start there. So we want to push 0 onto our stack so that we can enter the first room, the 0th room. Now we want to say so long as there are elements to process on the stack, so as long as its length is greater than 0, we want to iterate. Now what we want to do is we want to pop whatever room number is on the stack. So we'll say room number is going to be stack.pop. Now we'll have our step where we process the node, which we will come back to in a minute. Then we also want to figure out how we can continue doing our DFS. So we want to say what rooms can I access from the current room. So we can say new room numbers. These are like new room numbers that we can now access. It's going to be whatever keys we have in the current room. So it's going to be rooms at room number. Then we want to iterate through all of those. So new room numbers dot for each new room number. Oops, this should be singular. And we want to say if we have not visited the new room number, I'll talk about why that's important in a second, but we want to push that new room number onto the stack. For a second, we can forget about the if condition. All we really want to say is go through all of the keys that we've found. You could name this keys as well. Honestly, either is probably fine. Yeah, it doesn't particularly matter that much. We want to say go through all the keys or new room numbers that we can now access. Actually, I'm going to change this to be keys, and we'll change this to be key. You can use Command D in VS Code to highlight multiple of the same thing and change them all at once, which is pretty helpful. But okay, so we're grabbing all the keys that work for the current room number. We're saying go through all of them and push them onto the stack. One thing is that there might be two different paths to the same room, and if that happens, we don't want to process that room twice. So that's why we have the if condition. We're just saying if we have not already visited this room, or the key that points to this room, then add it to the stack. If we have visited it, just forget about it. Don't do anything else. Okay, so this gives us the boilerplate of our BFS. The only thing we need to figure out is what do we want to do for each of our rooms as we hit them. Well, in this problem, all we want to do is just check if they all can be visited. So what we can do is just say set visited at that room number to be true. By default, when you just create a new array like this, all of the values are undefined, which is falsy in JavaScript. But now you're setting it to be true, so that way every node that we hit will have a value of true here. And that's it for DFSing through this graph. The only thing remaining is that after our DFS, we have to actually return our answer. So, so if every room has been visited, then you want to return true, because we can visit all rooms. Otherwise, we return false. There are probably many ways you can do this with like built-in array methods or whatever. It doesn't particularly matter, so I'm just going to do a pretty straightforward way. I'm just going to iterate through every element of the visited array and just say, if we ever find one that's false, just go ahead and return false, because if any single room cannot be visited, then we return false. So we'll say if visited at I is false, so we can do if not visited at I, just go ahead and return false right away. If we iterate through the entire loop and we never return false, then we know that every single room that's represented in our visited array can indeed be visited, so we return true in the end. Okay, let's go ahead and verify that this works. So we have our example up here. We know that the output should be true, so let's see if it works. Come over here, we run our file, and we get true. Now, let's say we remove this right here. So now all of a sudden you cannot access room number 4. It should be false. Okay, great. So it looks like that's working. Let's talk about the complexity here. So we want to start by saying v is equal to the number of vertices, which is equal to the number of rooms, and e is equal to the number of edges, which is equal to the number of keys in our graph. So our time complexity is O of v plus e, our space complexity is O of v. Our time complexity, you can see that in the worst case, every single node is going to be added to the stack, so that's O of v time in total. And then we're going through every edge for each node in the worst case scenario right here. So in total, we are doing O of e in terms of the time there. So the overall time complexity is O of v plus e. Our space complexity, you can see this visited array has the same length as the rooms array, which is going to give us O of v space complexity. And we also know that with the DFS, it's possible that you have 0, which points to room 1, which points to room 2, which points to room 3, which points to room 4, and so on. And in that case, our stack would have 0, 1, 2, 3, 4, and so on, all on top of it at one point in time. So that's where the O of v worst case space complexity comes from. You can also change these variables to be more dynamic for the question. So you could say you could do R for the number of rooms and K for the number of keys. Then it's going to be O of R plus K time and O of R space. It doesn't really matter. Maybe it's a little more nuanced to the context of the question, but the complexity in the end ends up being the same. All right, that's all for this video, and I'll see you in the next one.